Greetings, campers. Welcome back. So here we are. We're going to do a quick PowerPoint to start off with a little bit of the notes from that was originated from the workbook with a little bit added on. And then we'll do some of the workbook problems for section 5-1. We're not going to do all the problems today. We'll start on question 7 and go up to about 15. So we'll see where we get, and then maybe a little bell work afterwards to practice the problem solving just a little bit. So the first slide here is dealing with the self-identity problems of light, dealing with, is it a light, is it a wave, or is it a particle, and has the properties of both. I think everybody got that question right in the last one. So in terms of the longer wave, lower energy, up till visible, generally, Kennedy Oswald, they're going to tell you, generally we treat that as a wave more than a particle. It just makes sense because that's where we deal with those aspects. So we're going to start dealing with the wave model, first of all, in chapter 5, and then move on more to the particle stuff in chapter 6. So just a reminder that light is EMR. In physics, light is called electromagnetic radiation, which is also then referred to as EMR. EMR is a natural phenomena that can be produced and detected by technological means. So we can produce EMR, we can detect EMR, that which is visible and that which is not visible. So in terms of the nature of the EMR is always caused by accelerating charges. And we don't like to throw that word always around too often in science, but that's one where it's fairly constant. Accelerating, though, can be speeding up, slowing down, or going at constant speed, but changing directions. So EMR is always caused by accelerating charges that speed up, slow down, or change direction. So the greater the acceleration, the greater the charge. So there's a higher degree of acceleration taking place. If you change its direction more than you do less, then there'll be higher energy of the EMR. So it's going to be at the higher end of the scale. So again, if we've got radio all the way to gamma here, radio, micro, infrared, visible, ultraviolet, X-rays, and gamma, the ones that are high energy are a greater degree of acceleration. Also, when there's higher energy, there's higher frequency. So here's the frequency, 10 to the 23rd, as opposed to 10 to the 3 down at this end, at the longer wave end. And again, the shorter the wavelength, so higher acceleration, shorter wavelength. But the speed of EMR is pretty much constant. What we use V, we can always also use the letter C specifically for the speed of light, is 3.00 times 10 to the 8 meters per second. That is in air or in a vacuum. So we're going to find later on that it does slow down when it goes through a more dense medium, such as glass or water or diamond. We'll deal with that as we get to it later on. So again, the nature of the EMR we talked about yesterday, they are transverse waves. Remember, transverse versus the longitudinal waves, or the compressional waves is what I like to call them. But EMR are going to be transverse waves. Sound would be an example of longitudinal waves. Contain a changing electric field component, which induces a changing magnetic field, which induces a changing electric field, and so on. And so this is a great diagram to show here's the direction of the propagation of the C, or we could have put a V. There's going to be perpendicular to that, it will be a changing electric field and a changing magnetic field. So a magnetic wave and electric wave. So that's how it self-propagates itself. And again, we've got that magnetic field and electric field demonstrated there, both perpendicular to the direction of propagation itself. So wave properties, we've got some long waves at the end here, getting very, very short. Some of these are 10 to the 3,000 kilometers long and getting smaller and smaller as you go along. So what exactly we talk about when we talk about the source? So the source is anything that vibrates or creates a disturbance and a wave. In terms of EMR, what is the source of it? It's going to again be the accelerating charges. Accelerating charges are always the sources of those waves. So the medium is the substance that a wave travels through. EMR, unlike other waves, just other than the mechanical waves all need a medium. EMR does not require a medium, which was one of the problems when it came to the early days of discussing wave or particle, because they knew that light traveled through space. They believed space was a vacuum, and other waves are not able to travel through space. So the speed of wave is a constant in a vacuum or in air. To 3 significant digits, 3.00 times 10 to the 8 meters per second. It's a little bit slower in air than it is in a vacuum, but not to 3 sig digs. But when you change the substance to more dense mediums, then you have to start following Snell's law. And what's going to happen is that the speed is going to slow down. It's going to bend. That's what this angle sine theta 1, sine theta 2 is about. The wavelength is going to change. The index of refraction of the medium relates to these ends. We're going to see that. But the one thing which is constant, when you change a medium, the velocity changes and the wavelength changes, but the frequency is always constant. So when light moves from air into glass, it's going to slow down, it's going to bend, the wavelength is going to change, but the frequency will stay the same always. So some other wave properties that are important. Wavelength. Wavelength is the distance from crest to crest, or you can measure it from trough to trough, or from this point to the same point on an adjacent wave. So the wavelength is symbolized by lambda. It's the distance in meters from one point on a wave to the same point on the next wave, crest to crest, trough to trough, etc. Now you see the height of the wave is from this equatorial, this baseline, up to the top of the wave, or would be equal to the bottom of the trough. This would be the positive amplitude, and down here would be, of course, the negative. Frequency. Frequency is the number of waves to pass a fixed point per unit time, usually waves per second. In waves per second, it's measured in hertz. 1 hertz is equal to 1 over seconds. So frequency is symbolized by small letter f, measured in hertz. It's how many waves pass a particular point per second. Now we have some very important wave formulas. We have the universal wave equation, which is true for all waves and definitely important for light. V equals f times lambda. So the frequency times the lambda is equal to the speed of light, which is a constant again, 3.00 times 10 to the 8. So if we need the lambda and we know the frequency, we can go 3 times 10 to the 8 divided by frequency to get lambda, or vice versa for frequency. Another very important one, which goes hand in hand, relates the period to the frequency. Now you'll probably, hopefully, remember from Physics 20 that the period is how long it takes for one complete cycle to go by. So in a circle, it was 1 circle. In a pendulum, it was 1 complete swing and back. But in terms of waves, it's how long it takes for 1 wave to get by. So the way that period relates to frequency is that period is the inverse of frequency. So the inverse of frequency would be the period, or the inverse of period would equal to frequency. And we're going to use that again, probably starting Friday. And that's that part, folks. So now we're going to go over some workbook problems. We're just going to go number 7 till number 15. It's again section 5.1. So open up your workbooks to page 190 and we'll get working on these. So we're going to start with question number 7 and do all just the quantitative questions. And what you're going to find is these are quite easy, a lot of repetition. And there's a couple of reasons for that, and we'll talk about those as we go, some of the subliminal objectives of doing these questions. We want to calculate the period when we know the frequency. I'll remind you that the formula that relates period to frequency is that they're inverses of each other. So period is equal to 1 over frequency. The frequency was given as 4.23 times 10 to 14 hertz. So we're going to put in that number of 4.23 second exponent 14, and we're just going to hit our inverse key. That's this guy right here. That guy right there. All right, now nice. Sorry, folks. Hit the inverse key, and we'll enter. We get 2.36 times 10 to the minus 15 seconds. So that's not very long for one wave to get past it. Take a second and copy that down. So question number 8, we're going to utilize our universal wave equation. V is equal to F times lambda, but in this case we want to find lambda. So we divide both sides by a frequency. All EMR, always, it's going to be 3.00 times 10 to the 8 meters per second. The frequency here was given as 5.5 times 10 to the 14 hertz. Punch that into our calculator. 3 second exponent 8 divided by 5.5 second exponent. Oops. Exponent 14. Enter. 5.45 times 10 to the minus 7 meters. So I'm going to leave my answer in meters. You see the Kennedy and Oswald, I like to use the nanometers. Nano means times 10 to the minus 9. Again, if you have some trouble with those, look back at your formula sheet. We're going to go through a lot of unit conversions today. And we're just going to take our exponent values as we go through them. So check those out as you go along. Okay, question number 9. First, we want to find the frequency. We're going to go V is equal to F times lambda. So the frequency is equal to V over lambda. The V, the speed of light, 3 times 10 to the 8. Lambda 6.53 times 10 to the minus 10 meters. Very short waves. Punch that in our calculator. 3 second exponent 8 divided by 6.53 second exponent minus 10. We get a value of 4.59 times 10 to the 17 hertz. So there's our question A, our frequency. Now we want to find the period from that. Remember the formula to relate period and frequency. Period is the inverse of frequency. 4.59 times 10 to the 17 hertz. So I have that number in my calculator. I'm just going to hit my inverse key. Enter. I get 2.18 times 10 to the minus 18. Period of one wave. So hit pause, take a few seconds, and get that all copied down. So here we've got a street lamp. We know the speed of light in air is going to be 3.00 times 10 to the 8. We're given the wavelength. We want to find the frequency, so we rearrange that for frequency. Again, 3.00 times 10 to the 8. It's okay to be lazy and just put 3 times 10 to the 8 if you wish. 590 nanometers. So again, that's times 10 to the minus 9. If you wanted to go 5.90 times 10 to the minus 7, that would be true. But don't mess with that. That's where you make a silly mistake quite often. So we're going to enter that into our calculator. We get a frequency of 5.08 times 10 to the 4. Sorry, that's 14 on that calculator. And that looks like the right answer. Take a second, hit pause, copy that. So in this case, we're going to take this laser at 680 nanometers, V equals F over lambda. So, sorry, V equals F times lambda, F equals V over lambda. Substitute in 3.00 times 10 to the 8 divided by 680 times 10 to the minus 9. When I punch that in to my calculator, I get 4.41 times 10 to the 14 hertz. I know that that's definitely in the visible range because it's a laser. Turns out I looked it up in the Google. That's red. That's the range for red. Question number 12. Some people have the ability to see greater wavelengths than most, all the way from 380 nanometers to 780 nanometers. Find the frequency of the longer wavelength. So if V equals F times lambda, then frequency equals V over lambda. Still 3 times 10 to the 8, folks. And the longer wavelength, 780, is longer than 380. Remember your times 10 to the minus 9. So I said earlier when we were starting this question that these questions that there's two things that they want to, the reason there's so much repetition, two things other than the formulas. Number one is to really get into your head that that is the speed of light. That's the constant, the speed of light. The other is to get you working a little bit with some of these units and being comfortable switching back and forth from nanometers to meters. Remember, in these equations, we have to be in SI, has to be in meters. So when I punch that into my calculator, I get 3.85 times 10 to the 14 hertz. Nice work. So question number 13, many cordless phones, we're not talking about cell phones, we're talking about the wireless phones in your landlines in your house. And baby monitors actually use a radio frequency at about 2.4 gigahertz. Calculate the magnitudes of the phone's wavelength. So again, V equals F times lambda. Lambda is V over F. The V, a constant, 3 times 10 to the 8. The next trick on this is converting giga. So if you look that up on your formula sheet, it's going to tell you giga is a billion. So it's 10 to the 9. So when we punch that into our calculator, we get 0.128, but to 2 sig digs meters. And again, Kennedy Oswald did move that decimal over 2 and made it into centimeters for their key, but I prefer just to leave it in meters. All right, so number 14. AM radio stations broadcast between 535 kilohertz and 1700 kilohertz, while FM radios are more in the 88 megahertz to 108 megahertz. Local radio station broadcasts at a frequency of 90.9 megahertz. So it's putting it in the FM range. Calculate the wavelength of that particular radio station. So V equals F times lambda. Lambda equals V over F. So we'll substitute in 3.00 times 10 to the 8. And then for the frequency, the 90.9 megahertz, if you look at your formula sheet, it's going to tell you mega is a million times 10 to the 6. So 90.9 times 10 to the 6. Punch that in your calculator, and you're going to get 3.30 meters. So question B, if that tells us the wavelength, the distance of one wave is 3.30, how many radio waves are you going to get over this distance of 1.5 kilometers? So I'm going to just use a simple factor label method, something like Mr. Bullock's pick a fence. How many waves is what we're looking for? So we look for the number of waves we're looking for. What are we trying to convert? Trying to convert 1.5 kilometers, which is 1.5 times 10 to the 3 meters. Kilo means and then we multiply that thing we're trying to convert by our conversion factor. Our conversion factor is that the wavelength is 3.30 meters. So in other words, one wave is 3.30 meters, or 3.30 meters is one wave. How do we know what goes on the top? We know that it has to be waves because we want our final answer to be in waves. And we know that it has to be meters on the bottom because we need to find a way to cancel out those meters and get them out of there. So basically that's the same as saying 1.5 times 10 to the 3 times 1 divided by 3.30. And when we punch that into our calculator, we get 455 waves. Now I see that the keyed answer is 454 waves, but it was actually 454.5. So we rounded up. Oh, how many complete? There you go. That's why we didn't round. My apologies to Mr. Oswald, Mr. Kennedy. So for the last question here, number 15, quick sketches of graphs. Speed versus the frequency. What do we know about the speed of light? It's constant. It's a constant. What's that value going to be at? 3.00 times 10 to the 8. As we've seen through this, we've over and over again, if that is a constant. So if we wanted f, it was v over lambda. If we wanted lambda, it's v over f. They were on the opposite side, so they were inverses of each other. So as one goes up, the other goes down. So if we were to write that relationship out, it would be frequency proportionate to 1 over. If that's the case, that graph is going to look like a very gentle slope coming down like that. So that's it, folks. Number 15, 22 minutes. Sorry, that was longer than I thought it was going to take. Have a good one.